What if everything you see around you, the stars, the planets, even the empty space between them, is just a tiny fraction of a far grander reality? A reality where dimensions beyond our own exist, hidden from sight but pulsing just beneath the surface of the universe we think we know. It sounds like something straight out of a sci-fi blockbuster, like Interstellar or Stranger Things, but here's the twist. This idea isn't just Hollywood magic. It's a real scientific theory, one that's been debated by physicists for decades. And today, we're diving headfirst into the mystery of hidden dimensions, where they might be, how they could shape our universe, and why understanding them might rewrite everything we thought we knew about reality. Picture this: you're holding a piece of paper. To an ant crawling across its surface, that paper is its entire world, flat, two-dimensional, with no concept of up or down. But you see the bigger picture. You know that paper exists in a three-dimensional space with depth and height the ant could never perceive. Now, what if we're the ants? What if there are dimensions, layers of reality stacked all around us, invisible to our senses but just as real as the air we breathe? That's the tantalizing possibility hidden dimensions propose. And it's not just wild speculation. Theories like string theory and the holographic principles suggest these extra dimensions could be the missing pieces to some of physics' biggest puzzles, from the nature of gravity to the very fabric of spacetime itself. So why haven't we found them yet? Why don't we see these hidden dimensions unfolding around us? That's where things get even more fascinating. Some scientists believe these dimensions could be curled up, tiny beyond imagination, like a crumpled piece of paper viewed from a distance. Others think they might exist parallel to our own, separated by forces or membranes we don't yet understand. And then there's the mind-bending idea that our entire universe could be a projection from a higher dimensional reality, like a shadow cast by something far more complex. Over the course of this video, we'll unravel these theories, explore the experiments hunting for evidence, and ask the big question: if these dimensions are out there, what would it mean for us? Strap in, we're about to take a journey to the edges of science, where the known universe meets the unimaginable. To understand hidden dimensions, we first need to grasp what dimensions actually are. Think of them as the different ways we can move through space. A zero-dimensional world is just a single point, no length, no width, no depth. Picture a dot on a page, completely still, with nowhere to go. Now stretch that point into a line, and suddenly you've entered the first dimension. It's like drawing a straight path where you can only move forward or backward. Add another direction at right angles, and you've got the second dimension, a flat plane where shapes like circles and squares exist but with no thickness. This is where our ant on the paper lives, unaware of up or down. But we don't live in a flat world. The third dimension brings depth, turning those flat shapes into objects you can hold, like a cube instead of just a square. This is our everyday reality, where we can move left and right, forward and backward, up and down. Now, here's where it gets interesting. Time isn't just something that passes, it's actually the fourth dimension. Imagine a movie reel. Each frame is a snapshot of the third dimension at a particular moment. When you play it, those slices of time blend together into motion. That's how we experience the fourth dimension, not as a place we can visit, but as a continuous flow we're carried along by. So why can't we see or move through higher dimensions if they exist? One theory is that they're curled up incredibly small, like a drinking straw. From far away, the straw looks like a simple line, one-dimensional, but up close, you realize it's actually a cylinder with a circular dimension wrapped around it. If extra dimensions are like that, folded into spaces smaller than atoms, no wonder we've missed them. Another possibility is that we're trapped in our three-dimensional membrane, like characters in a painting who can't step outside their canvas. Higher dimensions could be just beyond our reach, influencing our universe in ways we're only beginning to uncover. The more we explore these ideas, the more we realize how much of reality might be hiding in plain sight. Einstein revolutionized our understanding of the universe when he revealed that space and time aren't separate entities but intertwined threads in a single fabric, space-time. Imagine tossing a bowling ball onto a trampoline. The way it warps the surface is exactly how massive objects like stars and planets bend space-time, creating what we feel as gravity. This was the heart of his general theory of relativity, a framework so powerful it predicted black holes and the bending of light decades before we could observe them. But here's where it gets even wilder. Einstein's work didn't just explain gravity, it cracked open a door to questions we're still grappling with today, like why gravity is so much weaker than the other fundamental forces. Think about it, a tiny magnet can lift a paperclip off a table, defying the gravitational pull of the entire Earth. That mismatch has puzzled scientists for over a century. One compelling explanation: gravity might be leaking into hidden dimensions. Picture a sponge soaking up water. If our universe is the sponge, gravity could be seeping into spaces we can't see, diluting its strength in our observable reality. This idea isn't just speculative fiction. It's a serious hypothesis in theoretical physics, supported by models like string theory, which requires extra dimensions to make the math work. Einstein's spacetime was four-dimensional, three of space, one of time. But what if there are more? Some theories suggest these extra dimensions could be compactified, curled up so tightly they're invisible at our scale, like the grooves on a vinyl record too fine for the needle to detect. Others propose they're vast but inaccessible, separated from us by cosmic walls called branes. Whether tiny or expansive, these hidden dimensions might hold the keys to unifying gravity with quantum mechanics, solving one of the greatest puzzles in physics. And while Einstein never lived to see these ideas take shape, his foundation made them possible proof that even the boldest theories grow from the shoulders of giants. Theodore Kaluza's 1919 paper landed like a quiet revolution in physics. At first glance, it seemed impossible. By adding just one extra dimension to Einstein's equations of gravity, Kaluza showed that electromagnetism could emerge naturally from the same geometric framework. Picture discovering that two completely different puzzles were actually pieces of the same grand design. Kaluza's fifth dimension wasn't just mathematical trickery. It suggested a profound unity between forces that shaped our universe, hidden in plain sight within the geometry of spacetime itself. But there was a glaring problem. If this fifth dimension existed, where was it? Enter Oscar Klein, who proposed a brilliant solution in the 1920s. Imagine an ant walking along a coiled garden hose. From a distance, the hose appears as a simple line, one-dimensional. But up close, the ant discovers a circular dimension wrapped tightly around the hose's surface. Klein suggested our extra dimension might behave similarly, curled up into a space so small, perhaps a billionth of a billionth the size of an atom, that even our most powerful instruments can't detect it. This compactification transformed Kaluza's abstract math into a tangible, if elusive, feature of reality. The implications were staggering. If correct, Kaluza and Klein had uncovered a cosmic shortcut, a way to unify fundamental forces by weaving them into the very fabric of higher dimensional space. Their theory became the prototype for modern attempts to reconcile gravity with quantum mechanics, showing how hidden dimensions could solve puzzles that had stumped physicists for generations. Yet for all its elegance, the theory had limitations. It couldn't explain why the fifth dimension remained hidden while others expanded, or how quantum effects might reshape these curled-up spaces. Still, their work lit a torch that would guide physicists through the 20th century, proving sometimes the most radical ideas emerge not from overturning old theories but from expanding them into unseen dimensions. String theory doesn't just suggest hidden dimensions might exist, it demands them. While traditional physics describes particles as tiny dots moving through space, string theory paints a far more intricate picture. Instead of points, everything in the universe could be made of unimaginably small, vibrating strings, each one a billionth of a billionth the size of an atom. And just like the strings on a guitar, the way they vibrate determines what note they play, except these notes aren't sound waves. They're the fundamental building blocks of reality itself. A string vibrating one way might become an electron, another could be a quark, and others might even carry the force of gravity. But here's where it gets mind-bending. For the math behind string theory to work, these strings can't just wiggle in the 3 dimensions we know. They need room to move, way more room. The equations only balance if the universe has at least 10 or 11 dimensions, with the extras curled up so tightly we'd never notice them in everyday life. Picture a spiderweb glistening with dew. To us, it's a flat, delicate sheet, but to a microscopic observer, each thread is a complex, knotted world of its own. That's how these extra dimensions could exist, hidden in plain sight, yet shaping the very fabric of reality. This radical idea completely upends the standard model of particle physics, which treats particles as zero-dimensional dots bouncing around like billiard balls. The problem: that model can't explain gravity's bizarre weakness compared to other forces. String theory offers a way out. Gravity might be leaking into those extra dimensions, thinning out its effect in our observable world. It's like trying to hear a whisper in a cathedral. The sound isn't gone, just spread too thin to grasp. Brian Greene's The Elegant Universe brought these ideas into the mainstream, comparing the cosmos to a grand symphony where every particle, every force, is just a different vibration of the same cosmic strings. But string theory isn't without its critics. Some argue it's more math than physics, a beautiful idea that's yet to make testable predictions. Others see it as the only path to unifying all the forces of nature under one roof, a theory of everything. Whether it's right or not, one thing's certain: if strings and hidden dimensions are real, the universe is far stranger and far more musical than we ever imagined. What if our entire universe is just a thin slice floating in something far larger, like a single page in an endless cosmic book? This is the startling premise of Brane world theory, which reimagines our 3-dimensional reality as a membrane, or brane, suspended in a higher dimensional space called the bulk. Picture a loaf of raisin bread fresh from the oven. Each raisin represents a separate brane universe like ours, embedded in the dough of the bulk. We're stuck on our raisin, unable to perceive the others, even though they might be mere millimeters away in higher dimensions. Lisa Randall, a trailblazing theoretical physicist, took this idea even further. She proposed that some of these extra dimensions could be warped like a funhouse mirror bending light. In her model, gravity, unlike other forces, isn't confined to our brain. It spills into the bulk, weakening its effect in our observable universe. Think of it like water soaking through a paper towel. Most of the liquid stays trapped in the fibers, but some seeps through to the other side. That's why gravity feels so feeble compared to, say, magnetism. It's not that gravity is inherently weak. It's just that most of its strength is leaking into dimensions we can't see. This warped geometry could explain another cosmic mystery: why the universe's expansion is accelerating. If branes collide or ripple in the bulk, the energy released might mimic the effect we call dark energy. It's like tossing a pebble into a pond. The ripples change the water's surface, just as hidden dimensions might warp the fabric of space-time itself. Randall's work doesn't just hint at unseen dimensions. It suggests they could be actively shaping the fate of the cosmos. The implications are dizzying. If branes exist, parallel universes might hover tantalizingly close, separated by less than the width of an atom, but in a direction we can't point to. Some theories even propose that the Big Bang itself was the aftermath of 2 branes colliding, like cymbals crashing in a silent symphony of higher dimensions. Whether these ideas hold up under scrutiny, they force us to confront a humbling truth. The universe we see might be just a shadow of something far richer, stranger, and more interconnected than we ever dreamed. What if hidden dimensions aren't microscopic at all? What if they're enormous, stretching millimeters or even larger, right under our noses? That's the bold claim of the AD model, proposed by physicists Nima Arkani-Hamed, Savas Dimopoulos, and Georgi D. Valle in the late 1990s. Unlike theories that tuck extra dimensions away in spaces smaller than atoms, their idea turns convention on its head. These dimensions could be vast enough to notice with everyday tools, yet we've missed them because they interact with us in only the subtlest of ways. Imagine living in a house where one room is invisible not because it's small, but because the door only opens for certain guests. That's how the AD model works. In their framework, our familiar three-dimensional universe is like a flat sheet drifting within a higher dimensional space. Gravity, unlike other forces, isn't confined to our sheet. It's free to spill into these larger dimensions, spreading out like ink soaking through layers of paper. The result, gravity appears weaker to us because its true strength is diluted across realms we can't access. It's the cosmic equivalent of trying to hear a conversation through a thick wall. You catch whispers, but the full voice is somewhere else entirely. But why wouldn't we notice something as big as a millimeter-sized dimension? Here's the catch: these extra spaces don't affect electromagnetism, light, or the nuclear forces that govern atoms. They're gravity-only zones. Think of it like a radio tuned to a single station. You could have 10 other channels playing, but if your receiver only picks up one, the rest might as well not exist. For us, bound to our three-dimensional brain, the only hint of these dimensions would come from gravity behaving oddly at tiny scales. That's where tabletop experiments come in. Scientists are now using exquisitely sensitive devices to measure the gravitational pull between objects separated by fractions of a millimeter. If gravity suddenly strengthens or weakens at these distances, deviating from Newton's inverse square law, it could signal a hidden dimension curving the fabric of space nearby. One experiment uses torsion balances, where tiny gold-coated plates twist toward each other under gravitational attraction, their movements tracked with laser precision. Others employ microfabricated cantilevers, thinner than a human hair, to detect forces that shouldn't exist in a purely three-dimensional world. The stakes couldn't be higher. If these experiments find even a whisper of extra dimensions, it would upend our understanding of reality. Suddenly, the universe becomes a place where the rules we've taken for granted, like gravity's strength or the speed of light, might just be local bylaws in a much stranger cosmos. And if they don't, well, that's science at its best. Even a null result pushes us to ask better questions, to dig deeper into the fabric of space itself. Because whether dimensions are curled up atomically small or hiding in plain sight, one thing's clear: there's far more to this universe than meets the eye. Forget about parallel universes being far away. What if they're right next to us, separated by a dimension we can't perceive? This is the spine-tingling possibility that emerges when you blend Hugh Everett's many worlds interpretation with the idea of hidden dimensions. Everett's radical theory suggests that every quantum decision spawns a new universe, like pages constantly being added to an infinite book. But here's the twist: those alternate realities might not just exist out there in some abstract sense. They could be stacked like pancakes in higher dimensional space, separated by a gap so tiny yet so profound that crossing it would rewrite the laws of physics as we know them. Take Schrödinger's infamous cat trapped in a box where it's both alive and dead until someone peeks inside. In the standard interpretation, observation collapses the possibilities into one outcome. But in Everett's view, the universe splits, one where the cat purrs, another where it doesn't. Now, imagine those outcomes aren't just abstract branches on a cosmic flowchart. They're physical places existing in dimensions perpendicular to our own. Picture a hallway with countless doors, each leading to a slightly different version of reality, all existing simultaneously in a hyperdimensional maze. The only reason we don't notice them: we're like ants crawling along a single thread in a vast tapestry, oblivious to the patterns woven just millimeters above our heads. This isn't just philosophical musing, it's a framework that could solve one of quantum mechanics' biggest headaches: why we never perceive superpositions in everyday life. If alternate realities are tucked into higher dimensions, it would explain why we only experience one timeline. It's not that the others vanish, they're simply displaced along an axis we can't access. Think of it like radio frequencies. All those signals are in the air around you right now, but without tuning to the right channel, you'd never know they existed. The implications are staggering. If true, every choice you've ever made, from what you ate for breakfast to whether you took that job, exists as a physical reality somewhere in the dimensional stack. Some physicists speculate that dark matter, the invisible glue holding galaxies together, might even be gravity leaking from these neighboring universes, tugging at ours from unseen directions. It's a reminder that the cosmos might be less like a solitary stage and more like a crowded theater, with every possible performance playing out at once, just on levels we're only beginning to imagine. Particle colliders like the Large Hadron Collider aren't just smashing atoms, they're hunting for cracks in reality itself. When protons collide at nearly the speed of light, they don't just produce debris, they create conditions so extreme they might briefly pry open hidden dimensions. Scientists watch for two telltale signs: missing energy and miniature black holes. Here's how it works. In normal collisions, energy is conserved, what goes in must come out. But if gravity is leaking into extra dimensions, some energy might vanish into them, like water spiraling down a drain we can't see. Detectors would spot an imbalance, a gap where energy should be but isn't. The fingerprint of a graviton, the hypothetical particle carrying gravity, slipping into unseen realms. Then there's the black hole scenario. If extra dimensions exist close to our own, their warped geometry could lower the energy threshold needed to form microscopic black holes, not the galaxy-swallowing monsters of sci-fi, but fleeting specks that evaporate instantly into Hawking radiation. Picture dropping a pebble into a pond. The splash is the collision, the ripples are particles we detect, but the real prize would be spotting the tiny whirlpool, the black hole. That proves space has hidden depths. So far, no luck, but the search has led to fascinating near misses like the 2012 Diphoton anomaly. That year, the LHC spotted an unexpected bump in data, a pair of photons with slightly more energy than standard physics predicted. For a breathless moment, theorists wondered if it was a Kaluza-Klein particle, a telltale echo of higher dimensions. In extra-dimensional models, particles like gravitons wouldn't exist as single entities but as towers of increasingly massive copies, like notes on a piano where each key plays the same chord but at a higher pitch. These Kaluza-Klein towers would manifest as heavier versions of known particles, leaving distinct energy signatures in collisions. The Diphoton blip fit the profile until more data revealed it was just statistical noise, a cosmic false alarm. Yet the hunt continues. Every time the LHC upgrades its power or precision, it's like polishing a lens to peer deeper into the shadows of reality. Even null results teach us something, ruling out certain sizes or configurations of hidden dimensions, narrowing the search. Because if these dimensions are real, their discovery wouldn't just rewrite textbooks, it would redefine our place in the cosmos, revealing that everything we've ever known floats atop a deeper, richer universe, one waiting to be uncovered, one collision at a time. When LIGO detected the first gravitational waves in 2015, it didn't just confirm Einstein's century-old prediction, it opened a backdoor into the hidden architecture of spacetime itself. These ripples, born from cataclysmic events like black hole mergers, stretch and compress space as they pass through Earth, leaving faint whispers in detectors. But what if those whispers sometimes carry secrets about dimensions beyond our own? Here's how it might work. In a purely four-dimensional universe, gravitational waves dissipate predictably, like ripples on a pond fading with distance. But if extra dimensions exist, some of that wave energy could leak into them, subtly altering the signal we detect. Picture shouting into a canyon. The echo you hear isn't just the original sound, but reflections bouncing off unseen walls. Similarly, gravitational waves passing through hidden dimensions might produce brainworld echoes, faint secondary signals trailing the main wave like cosmic afterimages. LIGO scientists have scoured their data for these anomalies, searching for telltale dips or repetitions in waveforms that defy conventional physics. Simulations reveal how dramatic these distortions could be. Imagine dropping two pebbles into a still pond. One sinks straight down, creating clean circles, while the other hits a submerged log, scattering ripples in jagged patterns. Hidden dimensions might twist gravitational waves in similarly unexpected ways, warping their waveforms like funhouse mirrors. Some models predict these extra dimensions could even split a single gravitational wave into multiple frequencies, as if the universe itself were playing a chord instead of a single note. The stakes are immense. If LIGO or future observatories like the Einstein telescope catch one of these distorted signals, it wouldn't just hint at extra dimensions, it could map their shape and size. A waveform's exact deformations might reveal whether dimensions are curled up like tiny spirals or stretched into vast, unseen landscapes. It's like listening to a symphony and suddenly hearing an instrument no one knew existed, its notes revealing the acoustics of a hidden concert hall. Yet the search is needle in a haystack hard. Background noise, detector limitations, and the sheer rarity of massive cosmic collisions mean definitive proof remains elusive. But with each new detection, the odds improve, and if that breakthrough comes, it would mean gravitational waves aren't just messengers of distant collisions, they're telegrams from the multidimensional edges of reality itself. What if our three-dimensional reality is just an elaborate illusion, a cosmic projection cast from a two-dimensional surface like a hologram on a credit card? This mind-bending possibility, proposed by Nobel laureate Gerard T. Hooft, turns our understanding of dimensions inside out. The holographic principle suggests that everything we perceive, every star, every galaxy, even your own hands typing this comment, might actually be encoded on a distant, flat boundary, with our rich 3D experience unfolding like a movie projected from its surface. Picture one of those security holograms on a credit card. Tilt it, and you see a 3D eagle or globe floating above the plastic. But here's the catch: that image isn't really in the card. It's reconstructed from microscopic grooves etched onto its 2D surface, a flat code that creates depth through perspective tricks. Now stretch this idea to cosmic scales. The holographic principle argues that our universe works the same way. All the information needed to describe every particle, every force, even your memories, could be smeared across a vast, distant boundary, like the event horizon of a black hole, with our 3D world being its decoded projection. This isn't just philosophical sleight of hand. It solves one of physics' most stubborn paradoxes, the black hole information problem. When matter falls into a black hole, classical physics says it's gone forever, violating quantum mechanics' rule that information can never be destroyed. But if that information isn't actually inside the black hole, but painted onto its 2D event horizon like a cosmic fingerprint, the paradox vanishes. It's like burning a book but having its contents magically preserved in the ashes pattern. The math behind this is staggeringly elegant. Just as every point on a hologram surface contains fragments of the whole 3D image, every patch of a black hole's event horizon could hold fragments of the universe's data. Leonard Susskind, who expanded T. Hooft's idea, compares it to a PowerPoint slide compressed to its smallest possible size. The file looks like gibberish up close, but when projected, it reveals a coherent picture. Similarly, the universe's true source code might exist in a compressed, lower-dimensional form, with our reality as its high-definition playback. Critics argue that if we're living in a hologram, there should be detectable pixelation, a fundamental limit to how sharp reality can get. Some quantum gravity models predict this graininess would appear at the Planck scale, 10 trillion times smaller than an atom. Others suggest it might manifest in subtle distortions of distant starlight like cosmic static. So far, no such evidence has surfaced, but the search continues. Whether the holographic principle holds up or not, it forces us to confront a humbling truth. The universe might be far weirder and far more economical than we ever imagined, a masterpiece painted on the thinnest possible canvas. Dark matter might be the universe's ultimate ghost, something that shapes galaxies, bends light, and outweighs visible matter 5 to 1, yet refuses to interact with us in any way we can directly detect. But what if it's not just shy? What if it's literally trapped somewhere else? One tantalizing possibility is that dark matter isn't in our dimension at all. It's stuck in a neighboring brane or curled up in higher dimensional geometry, shaking hands with our world only through the faintest gravitational whispers. Think of it like a room full of people chatting while someone on the other side of a thin wall hums a tune. You can't see the singer, you can't shake their hand, but you feel the vibrations through the wall. That's how dark matter could work, bound to a parallel reality inches away in a direction we can't point to. Its presence only revealed when its gravity tugs on stars and galaxies from behind the cosmic curtain. This would explain why it's so elusive. Our telescopes and detectors are built to catch particles that play by our dimension's rules, but dark matter might be playing an entirely different game. There's precedent for this kind of ghostly behavior. Take neutrinos, those lightweight, charge-less particles that stream through your body by the trillions every second without a trace. They're famously hard to detect because they barely interact with ordinary matter, slipping through the atomic voids like fog through a screen door. Now imagine a particle even more aloof, one that doesn't just dodge atoms but exists partially or entirely outside our dimensional framework. If dark matter is like that, tethered to a hidden brane or vibrating in compactified dimensions, it would make neutrinos seem downright chatty by comparison. Some theories go further, suggesting dark matter particles could be higher dimensional objects called Kaluza-Klein states. These would appear to us as a series of increasingly heavy shadow particles, each a reflection of the same fundamental entity, vibrating in extra dimensions like notes on a piano where every key plays a darker, deeper version of the same chord. If these particles are heavy enough, they'd move sluggishly through space, clumping into the vast halos we observe around galaxies rather than zipping away like neutrinos. And because they'd interact through gravity alone, they'd leave no other trace, perfectly matching dark matter's eerie profile. The implications are staggering. If dark matter is a sign of hidden dimensions, its discovery wouldn't just solve a cosmic mystery, it would fling open a door to realms we've only theorized. Collider experiments might one day produce these shadow particles, their missing energy a clue to their escape into higher dimensions. Gravitational wave detectors could catch distortions in space-time caused by branes brushing against each other, their ripples encoding secrets of the multidimensional landscape. Even the distribution of dark matter in galaxies, how it clumps or streams, might carry the fingerprints of these unseen geometries. Of course, not all physicists are convinced. Some argue that dark matter could still be an undiscovered particle within our own dimensions, something like the hypothetical WIMP, or weakly interacting massive particle. Others propose modifications to gravity itself, like MUND, to explain galactic rotations without invoking invisible matter at all. But the brane world hypothesis offers something uniquely compelling. A way to tie together two of physics' greatest puzzles, dark matter and hidden dimensions, into a single, elegant framework. Whether this idea holds up or not, it forces us to confront a humbling truth. The universe we see, the stars, the galaxies, the cosmic web, might be just the surface of something far deeper. If dark matter is indeed the shadow of another dimension, then every galaxy, every cluster, every ripple in the cosmic microwave background is a message from a world we can't see, written in the only language that crosses the dimensional divide, gravity. And that changes everything. We think of time as an unstoppable river flowing forward at the same steady pace for everyone, everywhere. But what if that's just an illusion, a limitation of our three-dimensional perspective? Einstein showed us that time isn't a fixed backdrop to the universe. It's a dynamic, stretchable dimension woven together with space into a single fabric. And just as a piece of paper can be folded to bring two distant points together, some theories suggest we might one day manipulate time itself by tapping into higher dimensions. Enter wormholes, the cosmic shortcuts that could turn time travel from sci-fi fantasy into theoretical possibility. The math behind this is mind-bending yet eerily elegant. In 1935, Einstein and physicist Nathan Rosen realized that their equations for general relativity allowed for bridges connecting distant parts of spacetime tunnels through the universe's underlying geometry. Picture an ant crawling along the length of a straw. To reach the other side, it has to travel the full distance. But if you pinch the straw, creating a shortcut between the top and bottom, the ant could hop across in an instant. That's the essence of an Einstein-Rosen bridge, a fold in spacetime where the usual rules of distance and potentially time no longer apply. Christopher Nolan's Interstellar gave us a stunning visual metaphor for this with the Tesseract scene, a higher dimensional library where time becomes a physical dimension Cooper can navigate. While the film took artistic liberties, the core idea isn't pure fiction. Theoretical models suggest that if higher dimensions exist, they might allow for spacetime to curve in ways that make wormholes stable enough to traverse. The catch: you'd need something called exotic matter with negative energy to prop the tunnel open, preventing it from collapsing the moment anything tries to pass through. Here's where things get even wilder. If a wormhole linked two points in spacetime with different gravitational intensities like near a black hole, and a quiet patch of space-time would flow at different rates at each end. Step through one way and you might emerge centuries in the past, go the other, and you could leap millennia ahead. It's like having two clocks ticking at different speeds connected by a hallway where the rules of time bend to the geometry of higher dimensions. Of course, no one's found a wormhole yet, and the energy requirements to stabilize one are beyond anything we can currently imagine. But the mere possibility rewrites what time travel could mean. Instead of building a DeLorean or a spinning police box, we might one day navigate time by mastering the hidden folds of spacetime itself. Proof that the universe's greatest mysteries might not lie in the distant stars, but in the dimensions lurking just beyond our grasp. Hidden within the equations of string theory lies a shape so complex, it defies our three-dimensional intuition, yet it might hold the key to the universe's deepest secrets. Calabi-Yau manifolds are six-dimensional mathematical marvels, twisting and folding in ways that make M.C. Escher's drawings look simple. To understand how these shapes could compactify string theory's extra dimensions, picture a garden hose stretched across a field. From a distance, it appears as a one-dimensional line, but zoom in, and you discover its circular cross-section, a tiny, curled-up dimension hidden in plain sight. Calabi-Yau manifolds take this idea to the extreme, packing six extra dimensions into spaces so minuscule they'd fit inside an atom 1 billion times over. But why these specific shapes? The answer lies in their exquisite mathematical harmony. Calabi-Yau manifolds aren't just any random folds, they satisfy a set of precise geometric conditions that make them uniquely suited to string theory's needs. For one, they're Ricci-flat, meaning their curvature balances perfectly, like a soap film stretched taut without bubbles or wrinkles. This smoothness ensures the equations governing strings, those tiny, vibrating filaments of energy, remain stable across all dimensions. Imagine trying to play a violin on a warped, bumpy surface. The notes would distort unpredictably, but on a Calabi-Yau manifold, strings vibrate cleanly, their harmonics producing the cosmic symphony of particles we observe. Visualizing these structures is where things get truly mind-bending. Since we can't perceive 6 dimensions directly, mathematicians project them into 3, creating surreal, lattice-like sculptures that hint at their higher dimensional beauty. Some resemble intricate coral reefs, with holes and tunnels looping through themselves in impossible ways. Others look like crystalline snowflakes grown wild, their symmetries echoing the patterns found in quarks and electrons. These aren't just artistic flourishes. Every twist and cavity in a Kaluza-Klein manifold influences how strings move within it, effectively programming the properties of particles. The size of a hole might determine an electron's mass. The angle of a fold could set the strength of the electromagnetic force. It's as if the universe's rulebook were written in the geometry of these hidden shapes. The implications are staggering. If Kaluza-Klein manifolds are real, then every law of physics, every particle, every force might just be the echo of strings dancing through dimensions we'll never see. That's the power and the poetry of this idea. The universe's most fundamental truths could be hiding not in equations alone, but in the silent, shimmering contours of spaces beyond our imagination. Long before particle colliders or quantum equations, ancient civilizations were already wrestling with the idea that reality might have hidden layers. Take the Kabbalah, Judaism's mystical tradition, which describes the universe as a tree of life with 10 sephirot, spiritual dimensions or emanations through which divine energy flows. These aren't just symbolic, they're a blueprint of creation, each sephirah representing a different aspect of existence, from wisdom to compassion to the physical world we inhabit. Picture a cosmic ladder where every rung is a dimension of spiritual and material reality, all interconnected. Sound familiar? It's eerily close to string theory's 10 or 11 dimensions, where vibrations in higher dimensional space dictate the laws of our universe. Hindu cosmology takes this even further. The ancient Vedas speak of 11 dimensions, 3 familiar spatial ones, time, and 7 hidden realms beyond human perception. These aren't abstract ideas, they're described as parallel worlds, each with its own laws and beings, stacked like layers of an onion. The Bhagavata Purana even details beings who perceive time differently, living for what we'd call millennia in what they experience as days, a striking echo of Einstein's time dilation near black holes. What's remarkable isn't just that these traditions imagined extra dimensions, but how they framed them, not as cold mathematical constructs, but as living, breathing aspects of a conscious cosmos. Then there's Plato's cave. In his famous allegory, prisoners chained in a cave see only shadows on the wall, mistaking them for reality. When one escapes and sees the 3-dimensional world outside, they realize the shadows were flat projections of a richer truth. Swap cave for Brane and shadows for particles, and you've got a 2,000-year-old metaphor for the holographic principle, the idea that our 3D universe might be a projection from a 2-dimensional boundary. Plato wasn't just talking about ignorance, he was hinting that what we perceive as reality could be a limited slice of something far grander. But here's where ancient wisdom and modern physics diverge. Mysticism often treats hidden dimensions as realms of spirit or consciousness, while science seeks mathematical rigor and testable predictions. Kabbalah's sephirot guide moral growth. Hindu cosmology interweaves physics with theology. Yet both share a profound insight. The universe is more layered than it appears. Whether through meditation or mathematics, humanity has always sensed there's more to the story, that behind the curtain of the everyday lies a stage vast enough for countless dimensions, each playing its part in the grand performance of existence. What if UFOs aren't spacecraft from distant planets but visitors slipping between dimensions right in front of us? The idea sounds like science fiction, but it's been taken seriously by some of the most meticulous minds in science. Take Jacques Vallée, the French astrophysicist who helped NASA map Mars before turning his attention to unexplained aerial phenomena. After analyzing thousands of UFO reports, he noticed something strange. these objects don't behave like physical craft obeying known physics. They appear and vanish instantaneously, change shape like liquid metal, and sometimes leave no radar trace, almost as if they're phasing in and out of our reality. Vallé's radical hypothesis: UFOs might not be extraterrestrial at all. They could be interdimensional phenomena, manifestations of intelligences operating in realms beyond our perceptual limits. Think of it like watching a 2D shadow puppet show. To the characters on the wall, the hand casting the shadow is an incomprehensible, godlike presence appearing, transforming, and disappearing at will. Now flip that analogy. What if UFOs are higher dimensional shadows, projections of entities or technologies moving through dimensions we can't access? This would explain their erratic behavior, like the infamous 2004 Nimitz encounter, where pilots described a tic-tac-shaped object accelerating from 0 to hypersonic speeds without a sonic boom. In our 3D world, that's impossible. But in a higher dimensional framework, the craft might be dipping into folded space-time, effectively taking shortcuts through dimensions we can't perceive. Even the Pentagon's UAP task force has cautiously acknowledged these possibilities. Their 2021 report listed transmedium objects, UFOs moving seamlessly between air, water, and space, and admitted some exhibit physics-defying capabilities. While they avoid speculating on origins, the data aligns oddly well with Vallé's ideas. Historical accounts add another layer. Medieval paintings show sky shields eerily resembling modern UFOs. 19th century newspapers reported airships with glowing lights decades before human flight. If these weren't alien visitors, could they have been glimpses of something slipping through dimensional cracks? But here's the crucial caveat: extraordinary claims require extraordinary evidence. The interdimensional hypothesis walks a razor's edge between cutting-edge physics and pseudoscience. Without reproducible data or a mathematical framework, it risks becoming a modern myth, a placeholder for mysteries we don't yet understand. That's why scientists like Vallée insist on rigorous analysis, distinguishing between wild speculation and testable theories. Perhaps future experiments like quantum gravity probes or hyperdimensional imaging could detect bleed-through from adjacent dimensions. Until then, the truth remains tantalizingly out of reach, hovering just beyond the borders of our three-dimensional perception. If our universe is just an advanced simulation running on some higher dimensional computer, does that make hidden dimensions the processing power behind reality? Philosopher Nick Bostrom's famous simulation argument forces us to confront this unsettling possibility that we might be living in an ancestor simulation created by a civilization vastly more advanced than our own. But here's the twist: if those creators exist in higher dimensions, their reality wouldn't just be more advanced. It would be fundamentally different in ways that make our three-dimensional existence look like a pixelated shadow of the real thing. Think of how we play open-world video games today. Every mountain, every raindrop, every blade of grass is rendered from a mathematical code, a simplified representation of a far more complex physics engine humming beneath the surface. Now imagine that engine doesn't just simulate 3 dimensions, but 6, 10, or more, collapsing them into a 3-dimensional projection for our limited perception. Suddenly, hidden dimensions aren't just theoretical curiosities, they're the raw computational framework our simulated universe is built upon. This idea flips the script on everything. Quantum indeterminacy, where particles exist in multiple states until observed, might not be a fundamental law. It could just be lazy rendering, like a video game only loading detailed textures when a player looks directly at them. Dark energy, perhaps the simulation's way of patching glitches in spacetime's expansion rate. Even déjà vu could be a buffer error, a momentary hiccup where the system accidentally replays a cached memory. But the deepest question isn't technical, it's existential. If we're simulations, do our choices matter? Some argue yes, that a civilization sophisticated enough to run such simulations would likely program genuine consciousness into its creations, making our experiences no less real for being coded. Others counter that it reduces all meaning to an illusion, like NPCs in a game believing they have free will. The wildest part we might never know. A simulation sophisticated enough to fool us would have no obvious bugs, just as a character in the Matrix wouldn't notice the code unless the architect slipped up. Yet some physicists speculate that if our universe is a simulation running on higher dimensional hardware, there could be subtle artifacts, mathematical rounding errors in physical constants, or unnatural pixelation at the Planck scale. Others hunt for cheat codes, fundamental limits like the speed of light, that might reveal the simulation's rule set. Whether this hypothesis terrifies or exhilarates you, one thing's clear: it transforms hidden dimensions from abstract theory into something far more visceral. They're no longer just curled-up geometric spaces, they could be the backstage of reality itself, where the universe's source code is written in a language we're only beginning to decipher. Frank Wilczek had a thought so bizarre even he hesitated to share it. What if crystals didn't just repeat in space, but in time? Normally, crystals like diamonds or snowflakes captivate us with their orderly atomic lattices patterns that repeat over and over in 3 dimensions. But Wilczek, a Nobel-winning physicist, wondered, could matter also form structures that repeat rhythmically in the 4th dimension? Time itself? The answer, it turns out, is yes. Welcome to the mind-bending world of time crystals, where the rules of physics dance to a whole new beat. In 2012, Wilczek proposed these exotic structures as a new phase of matter. Unlike ordinary crystals, which are frozen in static symmetry, time crystals are in perpetual motion without any energy input, like a clock that ticks forever without winding. At first, critics dismissed the idea as impossible, violating the sacred laws of thermodynamics. But then researchers at the University of Maryland and Harvard did the unthinkable: they built one. Using chains of ytterbium ions suspended in electromagnetic fields, they created a system where spins of atoms flipped back and forth in a never-ending cycle, locked into a pattern that repeated not just in space but in time. It was as if they'd carved a groove into the fabric of reality itself, making the universe's metronome visible for the first time. Here's the real kicker: time crystals don't just exist in time, they break it. Normally, the laws of physics look the same no matter when you observe them, but time crystals spontaneously shatter this symmetry, choosing moments like a pendulum choosing beats. It's as if time, usually an indifferent river, suddenly develops texture ripples and folds that hint at something deeper. Could this be a glimpse of higher dimensional physics peeking through? Some theorists think so. If time crystals can lock into rhythms beyond our usual flow of cause and effect, perhaps they're tapping into structures that resonate across dimensions we can't yet perceive. The experiments get even stranger. When scientists entangled multiple time crystals, the systems synchronized their pulses across distances, like pendulum clocks on opposite walls mysteriously swinging in unison. This eerie coordination, defying classical intuition, suggests a hidden layer of organization, almost as if the crystals are communicating through a dimension we can't see. Imagine 2 dancers separated by a curtain, moving in perfect sync without seeing each other, their rhythm guided by something beyond the stage. That's the enigma of time crystals. Their order doesn't come from the world we know, but from somewhere else, a somewhere that might just be the higher dimensional scaffolding of reality itself. Wilczek's wild idea has since blossomed into a frontier of physics, with labs crafting time crystals in diamond defects, superfluid helium, even quantum computers. Each discovery peels back another layer, suggesting that what we call time might be far richer and far stranger than a mere ticking clock. If these crystals are indeed windows into 4-dimensional physics, they're teaching us something profound. The universe doesn't just have dimensions. It sings with them in rhythms we're only beginning to hear. Black holes might be hiding the universe's most explosive secret, walls of searing radiation that vaporize anything crossing their event horizons. This terrifying idea, called the firewall paradox, emerged when physicists realized quantum mechanics and general relativity clash violently at a black hole's edge. But what if the solution lies in dimensions we can't see? Enter ER equals EPR, a conjecture so bold it reimagines spacetime itself. Proposed by Juan Maldacena and Leonard Susskind, this idea suggests that entangled particles, those spooky twins of quantum physics that mirror each other instantly across vast distances, might actually be connected by microscopic wormholes threading through higher dimensions. Picture two electrons born from the same quantum event, spinning in perfect sync even when light years apart. Normally, we'd say they're entangled, but ER equals EPR goes further. It proposes they're linked by an Einstein-Rosen bridge, a wormhole so tiny it's woven into the fabric of spacetime itself. This isn't just poetic metaphor. The math shows these wormholes could form from the quantum foam, those frothy fluctuations at the smallest scales of reality. Suddenly, entanglement isn't magic. It's geometry, a hidden tunnel through the multidimensional landscape we've been missing all along. Now, apply this to black holes. When matter falls past the event horizon, general relativity says it should smoothly sail toward the singularity. But quantum mechanics insists information can't be destroyed, meaning something must preserve the data of what fell in. Firewall's lethal barriers of high-energy particles were one grim solution. But ER equals EPR offers an elegant alternative. Maybe the interior of a black hole isn't a dead end. Maybe it's a bridge. Here's where dimensions come roaring back. If spacetime has hidden higher dimensional folds, a black hole's crushing gravity might pry them open, turning its core into a gateway. The matter that vanishes from our universe could emerge somewhere else another time, another dimension, or even another universe entirely. It's like squeezing a water balloon until it spurts out the opposite side, except the balloon is the fabric of reality, and the water is stars, planets, or anything else unlucky enough to take the plunge. Susskind visualizes this as a cosmic recycling plant. Black holes chew up matter and spit it out through wormholes into other regions of spacetime, with entanglement acting as the glue holding the whole system together. The firewall paradox evaporates because nothing ever truly hits the event horizon. It just transitions seamlessly into another part of the multiverse. Supporting this, some string theory models show black holes in higher dimensions can morph into fuzzballs, tangled knots of strings whose surfaces store information like a holographic hard drive, with wormholes branching inward like roots in hyperdimensional soil. The implications are staggering. If ER equals EPR is right, then every black hole could be a backdoor to somewhere else, with entangled particles serving as the secret handshake that keeps the connection stable. Distant quasars might be twinned through higher dimensional bridges we can't see. Even the Big Bang could have been a white hole, the inverse of a black hole, spewing our universe into existence from some other dimension's collapse. Yet challenges remain. No one's observed a wormhole, let alone proven it links entangled particles. The Planck-scale physics involved is far beyond our current tech. But upcoming quantum gravity experiments might look for telltale signatures like anomalous correlations between particles that only a hidden bridge could explain. Others are simulating wormhole dynamics in quantum computers, where entangled qubits mimic the conjectured spacetime tunnels. Whether ER equals EPR holds up or not, it's reshaped how we see reality's hidden scaffolding. Spooky action at a distance becomes cosmic engineering. Black holes transform from existential threats to potential portals, and the dimensions we once thought were silent, empty math. They might be buzzing with traffic, a vast interdimensional subway system where the trains run on entanglement, and the tickets are written in the language of gravity itself. The hunt for hidden dimensions hasn't been without its frustrations. Some of the most sensitive experiments ever built have come up empty-handed. Take the Large Hadron Collider. After smashing protons together with enough energy to recreate conditions a trillionth of a second after the Big Bang, scientists hope to catch a glimpse of particles like supersymmetric partners or Kaluza-Klein gravitons, telltale signs of extra dimensions. Yet decade after decade, the detectors remained stubbornly silent. No missing energy vanishing into unseen realms, no microscopic black holes winking in and out of existence. Just the humdrum chatter of known physics, as if the universe were playing keep away with its deepest secrets. Then there's gravity itself. If extra dimensions exist at microscopic scales, Newton's famous inverse square law should break down when objects get close enough for gravity to leak into them. Teams have spent years measuring the pull between exquisitely crafted gold plates, suspended just microns apart, distances where hidden dimensions ought to warp the force. Yet from Stanford to Washington, the results keep echoing the same verdict. Gravity behaves exactly as expected, even at scales 1,000 times thinner than a human hair. It's as if the dimensions theorists predicted simply folded their arms and refused to show up for the experiment. Even ghostly neutrinos, which can pass through light years of lead without a bump, have betrayed no hints of higher dimensional detours. Underground detectors like Ice Cube, buried deep in Antarctic ice, watch for neutrino oscillations that might reveal they're taking shortcuts through curled-up dimensions. But the data remains disappointingly ordinary, like tracking a marathon runner only to find they stuck rigidly to the paved roads instead of vanishing into secret alleyways. These null results aren't just dead ends, they're forcing physics into a corner. Supersymmetry, once the darling of particle theory, predicted a zoo of new particles that would balance the quantum equations and point to hidden dimensions. Yet with each failed search, the theory's parameter space shrinks, like a map being erased until only the most remote, fine-tuned possibilities remain. Some theorists now whisper about a nightmare scenario, a future where colliders find nothing but the Higgs boson, leaving dimensions forever just beyond reach. But here's the twist: absence of evidence isn't evidence of absence. Every null result sharpens the blade of inquiry, telling us where not to look and pushing ideas to their breaking points. Maybe dimensions are smaller than we thought, or curled in shapes too complex for current math to unravel. Or perhaps, like dark matter, they interact in ways we haven't yet dreamed of testing. The universe has a habit of hiding its cards until we ask exactly the right question, and right now we're still learning how to speak its language. Imagine a civilization so advanced it doesn't just explore hidden dimensions, it bends them to its will. This isn't just science fiction. It's the frontier of theoretical physics, where ideas like the Alcubierre drive and hyperdimensional Dyson spheres blur the line between fantasy and future possibility. Take warp bubbles, for instance. In 1994, physicist Miguel Alcubierre proposed a radical solution to faster-than-light travel. Instead of moving through space, you'd manipulate spacetime itself. Picture a surfboard riding a wave, except the wave is a distortion of the cosmos, compressing space in front of your ship and expanding it behind. You're not breaking the speed of light, you're cheating by contracting the distance. But here's the catch: making this work requires exotic matter with negative energy, something we've never observed. Or have we? Some theories suggest that if extra dimensions exist, their unique geometry might naturally produce the negative energy needed, like a hidden wellspring waiting to be tapped. Now stretch this idea even further. What if we could harness entire compact dimensions as power sources? Freeman Dyson's iconic megastructure, a sphere enveloping a star to capture its energy, gets a mind-bending upgrade in a multidimensional universe. Instead of building around a star, a hyper-advanced civilization might construct a Dyson network around a curled-up dimension, siphoning energy from the quantum vibrations rippling through it. Think of it like tuning into a cosmic radio station broadcast from higher dimensional space, where the signals are pure, untapped energy. Michio Kaku explores this in Physics of the Impossible, ranking such feats as Class Roman II impossibilities, technologies that don't break known physics but would require mastery over forces and scales beyond our current reach. The implications are staggering. If dimensional engineering became reality, the universe would transform from a vast, untouchable expanse into something more like a hyperdimensional workshop. Wormholes could be stabilized into transit corridors by threading them with exotic matter harvested from compact dimensions. Black holes might be repurposed as gateways or energy reservoirs, their singularities unraveled into higher dimensional strings. Even time itself could become a malleable resource, with chrono-engineering leveraging the fourth dimension like a dial to be adjusted, yet the hurdles are cosmic. Mastering dimensions would demand a command over gravity we can't yet fathom, perhaps through artificial black hole manipulation or quantum foam sculpting. The energy requirements would dwarf anything humanity has ever produced, and the risks, a miscalculation in warping space-time could rip a hole in reality itself, like tearing a page from the cosmic rulebook. But that's the allure of these ideas. They force us to confront the universe not as passive observers, but as potential shapers of its deepest layers. Whether these dreams remain impossible or become the blueprints of tomorrow depends on one question: are hidden dimensions the universe's best-kept secret or its ultimate toolkit? Why does our universe have 3 dimensions of space and one of time, a setup so familiar we barely question it? The answer might lie at the crossroads of 2 radically different perspectives: the anthropic principle and the cold logic of mathematical necessity. On one side, the anthropic argument suggests that 3 spatial dimensions are simply the only configuration where life as we know it could arise. In 2 dimensions, complex neural networks couldn't form. Traffic jams of intersecting signals would render brains impossible. In 4 or more, gravity's inverse square law would collapse stars and planets before life could emerge. Our existence, then, isn't just shaped by these dimensions, it's filtered by them, like a cosmic sieve that only allows observers to appear where the numbers align just right. But then there's Max Tegmark's audacious alternative, the mathematical universe hypothesis. In this view, dimensions aren't arbitrary settings, they're inevitable features of self-consistent mathematical structures. Tegmark argues that reality isn't just described by math, it is math with every possible equation playing out somewhere in the multiverse. From this perspective, our 3+1 dimensions might not be special at all, just one page in an infinite library of dimensional configurations, all equally real. It's like asking why a triangle has 3 sides. The answer lies in the definition of the shape itself, not some external choice. This raises a deeper question. Are dimensions fundamental building blocks of reality, or do they emerge from something more basic? Think of water waves. To a casual observer, waves seem like independent entities, but zoom in, and they're just the surface manifestation of countless molecular interactions. Similarly, space-time and its dimensions might be collective behaviors of underlying quantum threads, like the patterns in a tapestry emerging from hidden stitches. Some theories, like loop quantum gravity, suggest space-time could be granular at the smallest scales, with dimensions dissolving into a froth of connections. Others propose dimensions are dynamical, stretching and warping like living tissue in response to cosmic forces. The debate cuts to the heart of how we understand existence itself. If dimensions are fundamental, they're the stage on which reality performs. But if they're emergent, the stage itself is an illusion, a temporary scaffold built from subtler, stranger parts. Perhaps the truth lies between. 3 extended dimensions we experience plus time might be the most stable arrangement in a cosmos teeming with fleeting, crumpled possibilities. After all, even in string theory's kaleidoscope of 10 or 11 dimensions, only a handful unfurl to cosmic scales while the others stay tightly wound. So next time you move through space or check the clock, remember, those dimensions might not just be the rules of the game. They could be the game itself or the shadows of something far richer, waiting beyond the edges of our perception. Science fiction has a knack for making hidden dimensions feel thrilling, but how much of what we see on screen is rooted in real physics, and how much is pure Hollywood magic? Take Stranger Things and its eerie upside down. The idea of a parallel universe lurking just beneath our own taps into something physicists actually debate: brain worlds and quantum multiverses, but the show takes wild liberties. In reality, a neighboring dimension wouldn't be a foggy, monster-filled echo of our world. If it existed, it might be utterly alien, governed by different physical laws, with no recognizable landmarks or even the same number of dimensions. The upside-down spooky familiarity, that's fiction. The haunting possibility that such dimensions could brush against ours, that's where science gets interesting. Then there's Doctor Who, where the TARDIS famously defies physics by being bigger on the inside. While the show handwaves this with dimensional engineering, real theories like compactified dimensions or warp bubbles aren't far off. The idea of folding space to create extra room aligns with Kaluza-Klein's curled-up dimensions just scaled up to theatrical proportions. But here's the catch: stabilizing such a structure would require exotic matter with negative energy, something we've never observed. The Doctor's time-traveling police box is firmly in fantasy territory, but the underlying concept of manipulating dimensions, that's straight from the pages of theoretical physics textbooks. Compare this to Contact, the adaptation of Carl Sagan's novel, where Jodie Foster's character travels through a wormhole network. The film's portrayal of wormholes as tunnel-like pathways is surprisingly accurate to Einstein's equations. Even the disorienting time dilation and cosmic vistas she experiences align with general relativity's predictions. Where Contact stumbles is in the wormhole's artificial construction by aliens, something far beyond our current tech, but not outright impossible if higher dimensional engineering exists. Then there's Interstellar, a gold standard for scientific accuracy in sci-fi. Gargantua, the film's black hole, was rendered using actual equations from physicist Kip Thorne, resulting in the first realistic depiction of a spinning black hole's gravitational lensing. The time slippage on Miller's Planet, straight from Einstein's playbook. Even the Tesseract scene, where Cooper navigates time as a physical dimension, echoes legitimate, if speculative, ideas about higher dimensional spaces. Nolan's team didn't just guess, they collaborated with scientists to push speculative ideas to their limits without breaking known physics. The line between sci-fi and reality often comes down to artistic license versus testable theory. Shows like Stranger Things and Doctor Who prioritize storytelling over accuracy, sprinkling in just enough science to feel plausible. But films like Interstellar and Contact show how grounding spectacle in real physics can make the impossible feel tangible. The best sci-fi doesn't just entertain, it inspires us to ask, could this really happen? And sometimes the answer is closer to yes than we think. From the vibrating strings of string theory to the holographic edges of reality, the search for hidden dimensions has reshaped how we see the universe. String theory's elegant equations suggest 6 or 7 extra dimensions curled into Calabi-Yau manifolds, spaces so tiny they'd fit inside an atom, yet complex enough to dictate the laws of physics. Brane world models like Randall's Sundrum reimagine our cosmos as a membrane floating in a higher dimensional bulk, with gravity seeping into unseen realms. And the holographic principle flips the script entirely, proposing that our 3-dimensional experience might just be a projection from a 2-dimensional boundary, like a shadow cast by a deeper truth. Yet for all their mathematical beauty, these ideas remain unproven. No experiment has yet caught a graviton slipping into extra dimensions or detected the telltale warp of a neighboring brane. But that's the thrill of theoretical physics. The most radical ideas often start as whispers in the equations, waiting for technology to catch up. A century ago, black holes were mere pencil scratches on Einstein's notepad. Today, we photograph their shadows. Could hidden dimensions follow the same path from speculation to revelation? What's undeniable is how these theories stretch our imagination. They force us to confront the possibility that reality isn't just stranger than we suppose, it's stranger than we can suppose. As Carl Sagan once said, we are a way for the cosmos to know itself, and if these hidden dimensions are real, we might be on the brink of the greatest self-discovery of all, that the universe is vaster, more layered, and more mysterious than we ever dreamed. So what's your take? Do you think dimensions beyond our grasp are out there waiting to be uncovered in some futuristic lab or etched into the fabric of space-time itself? Drop your favorite theory in the comments and let's keep exploring the edges of the unknown together. The cosmos is listening.